Now we are on 2 and 3 dimension problems in trigonometry. Now if you look at the first one is in a right angle triangle, you can get all your three trig ratios there, and in the non-right angle triangle, the area of the triangle of AB sine C or of BC sine A, and so on. Now if you're looking at the sine rule, A over sine A is equal to B over sine B is equal to C over sine C, and we can choose whichever, whether we want the numerator to be the ratios, that will also be fine. And then you're going on to the cosine rule, A squared is equal to B squared plus C squared minus 2BC cos A, and so on. Then you can also have cos of A, and if you look at it strategically, it's minus A squared, and what you left in the numerator is B squared plus C squared, and your denominator is all over 2BC. Similarly, cos of B, that's how I would remember these formulae. It's minus B squared, and you're left with A squared plus C squared all over 2AC. Now, if you go down, I discussed this previously, where in any triangle, the area is 1/4 of the sum of two sides minus the third side, and it goes on to the perimeter, A plus B plus C. So if you let the A plus B plus C be the perimeter, you can actually get this formula. Now what is very interesting is you can actually test this formula, which works, and you can actually use all your rules, trigonometric rules, to actually prove or arrive at that formula. Right, in this question here, which is the problems on 2 and 3 dimension, in the adjacent figure, obviously we've got the figure below. PQ is one side of a tall building. SR and Q are 3 points on the same straight line, and SR is 100 meters. The angle of elevations of P from S and R respectively are 30 degrees and 80 degrees. So if we look at this problem here, we notice that the angle of elevations are, so if I can just try to see if we can put this into the 80 and 30. So what we really have now is if you look at there, we're looking at PQ. You wanted QR eventually, so we're looking at PQ over QR is equal to tan of 80 degrees, and then when you take this now, so you'll get QR is equal to PQ over tan of 80 degrees. And now we want to see how we can work with PQ in the broader sense as well. So we want to actually look at PQ and PR. Now if you look at PQ and PR, PQ over PR is sine of 80 degrees. PQ over PR is sine of 80 degrees. So PQ is equal to PR sine 80. Now PR is in that triangle, so if you use the sine rule there, PR over sine of 30 degrees is equal to 100 over sine of 50 degrees. So you would have known how we would have got the 50 degrees, 80 minus 30. So we've got PR. So we got PR is equal to 100 sine 30 over sine 50. Now we got sufficient information here, and then when we do our substitution for QR right at the top, so QR, and we've got, you remember, it's we've got PQ as well. PQ is equal to PR that, and PR, so we can do all our substitution, and we will get 100 sine 30 times sine of 80 degrees. Now the 80 degrees, when you look at the problem, there's no 80 degrees, sine of 80, the sine of 100, and we know they're equal. All over sine 50 tan 80. And if you look at the choices that you have, it is B. This problem here, AB is the diameter, therefore angle C is 90 degrees, and then we've got AB is produced to D such that BD is equal to BC, and we've got angle A is theta and BC is P. Now we want to find DC squared. So we are given that BC is P, so we've got P, and we've got angle A as theta, and then our question is to find DC. So if A is theta, then the angle B is equal to 90 plus theta. So what I'm going to do in this triangle here, we want DC squared, I'm going to use the cosine rule because I've got two sides in the included angle. So DC squared is equal to P squared plus P squared minus 2 times P times P times cos of the included angle, which is 90 plus theta. Now that gives you 2P squared. Now remember, cos of 90 plus theta is in the second quadrant, complementary ratio, and its answer is negative. Negative times negative is positive 2P squared, and the complement of cos is sine theta. So we've got an answer which is 2P squared into 1 plus sine theta. And then we'll now tackle the second part of the problem, which is 3.2.2. Then they said if DC is 12 and P is 4 root 3, calculate A and calculate angle A, which is theta, and AB. Right, so what we're going to do here now is to substitute. So DC squared is 144, P squared is 16 times 3, 48 times 2 is 96, into 1 plus sine theta, and when you work this out, you will get 1 plus sine theta is equal to 3 over 2, and then sine theta is equal to half, and theta is equal to 30 degrees. And then if you take our ratio now, sine 30 degrees in the right angle triangle is 4 root 3, that's P, over AB. So therefore AB will become 8 root 3. And that concludes that problem. Right, the problem here is 3.2. ABCD is a rhombus. A is equal to 2x, and the radius of the inscribed circle is r, so that is 2x, and the radius of the inscribed circle is r, and they want you to find the area of the rhombus. Obviously in a multiple choice you will get the options, and then you have to, after you're doing your work, you'd have to select the correct options. So looking at 3.2.1, and if you look at now r over OA, now we know that the diagonal bisects. So if you've got 2x here, each angle is x. So r over OA is equal to sine x. So OA is equal to r over sine x. Then we now can look at OB. Now if you look at this angles here, you will have x and 90 minus x. Why? Because the diagonals of a rhombus bisect each other at 90 degrees. So this will be, angle B will become 90 minus x. So we're looking at now OB is equal to, in a similar way, r over sine of 90 minus x. And sine of 90 minus x is r over cos of x. So now we are now going to find the we're going to find the area. Now all of us know that the area of a rhombus is half the product of the diagonals. So if we take the product of the diagonals, let's make it strategically 2OA times OB. Now 2OA will be 2r over sine x times OB, which is r over cos x. Now that can give you 2r squared over sine x cos x. And then we now are saying, let's assume we want to change this to one ratio, and that becomes 4r squared over 2 sine x cos x. I multiply the numerator and denominator by 2, and 4r squared over sine 2x. And then we've got the second part to the question. For what values of x will the rhombus have its maximum area? Now you may remember that it will as the x values change, and assuming the r remains constant, we are going to get, and we know if x is a smaller value, let's say x is 30 degrees, 2 times 30 is 60, and then we've got, or x is 15 degrees. 15 degrees, 2 times 15 is 30, that will be 8r squared. And as x becomes a larger angle, then the ratio becomes smaller. So therefore, what we are saying is that you must maximize that. And we know that the maximum value for sine is 1. So in other words, 2x is equal to 90 degrees, x is equal to 45 degrees. In this problem here, which is 3.12 on page 52, we've got PA is the tower, A, B, C are in the same horizontal plane, and angle ABC is x, and the angle of elevation of P from B is Z. So we are now going to show that H is 2D cos x tan Z. Now the connection in 3D problems, we can only look at the connection of the two triangles or two figures through a common side. So BA is common here, and we know that PA, which is the height over BA, is equal to tan Z. Tan Z. So PA, which is H, is equal to BA tan Z. Now we're going to take BA now and look at BA. We know this angle is x, so angle C is 180 minus 2x. And then we're now looking at using the sine rule, which says BA over sine of 180 minus 2x is equal to D, any one of those two sides, D over sine x. And then we are going to take the BA is equal to D times sine is positive in the second quadrant, sine 2x over sine x. Now that can be simplified to 2 sine x cos x. So 2D sine x cos x over sine x. So cancelling that, so you'll get BA is 2D cos x. So therefore H is equal to BA 2D cos x tan Z. And that concludes the problem there. Now remember, there are many other problems, and you'll notice in many cases I've said show, they will say it is equal to, and you'll have to choose the correct option.